Hello everyone, good evening. Let's start with today's session. So, right now we are covering this subject of process fluid mechanics, and in this, until now, we have studied this fluid statics, in which we have studied this power law model, then this force balances on any object within the fluid. Then in the last class, we were looking into this continuity equation and Bernoulli equation, basically mechanical energy balance. So today we'll be simply solving the questions related to each of these topics. A few questions will be related to Bernoulli equation, continuity theorem, and then there are some questions related to shear stress. So let's start with the first question for the day. So this is question number 20 from GATE 2015 chemical engineering paper. And the question is, two different liquids are flowing through different pipes of same diameter. In the first pipe, the flow is laminar with centerline velocity Vmax1, whereas in the second pipe, the flow is turbulent. For turbulent flow, the average velocity is 0.82 times the centerline velocity. Centerline velocity is Vmax2. For equal volumetric flow rates in both the pipe, the ratio Vmax1 upon Vmax2 is dash. So we will take a look on the video solutions of all the questions today. I will just share the video solution. Question 20. We are solving question number 20. Two different liquids are flowing through different pipes of same diameter, equal volumetric is dash. So over here we have been given that two different liquids are flowing through two different pipes of same diameter. This is my first pipe and this will be the second pipe. Now in the first pipe the flow is laminar and the centerline velocity we have been given as Vmax1, and for the turbulent flow the centerline velocity we have been given as Vmax2, and for turbulent flow we have been given that the average velocity, that is V average, is 0.82 times the centerline velocity Vmax2, and for equal volumetric flow rate in both the pipes, that is Q1 is equal to Q2, we have to find the ratio Vmax1 upon Vmax2. Now for laminar flow, we know that the velocity profile will be parabolic and it is given by u naught 1 minus r upon r whole square, and you can write it as 2 u bar, where u bar is the average velocity. So for laminar flow, the maximum velocity, that is Vmax1, will occur at r equal to 0. And also we can simply write that the average velocity will be half of the maximum velocity for laminar flow, that is V average will be 0.5 times of Vmax1. So we have the average velocity of the fluid in both the pipes. Now we can use that average velocity to find the volumetric flow rate by rho1 A1 V1 is equal to rho2 A2 V2, where rho1 and rho2 are the density of the fluid and they are same in both the cases. So this will get cancelled out. Now both the pipes have the same diameter. So the cross-section area, that is pi by 4 d1 square and pi by 4 d2 square, will be same. So this will also get cancelled out, and v1 and v2 are the average velocity. So we can replace the value of the average velocity in terms of this center line velocity, that is Vmax1 and Vmax2, using these two equations. So it will become 0.5 times Vmax1 is equal to 0.82 times of Vmax2. Now we have to find Vmax1 upon Vmax2. So it will become Vmax1 upon Vmax2 is equal to 0.82 upon 0.5. So that will be twice of 0.82. So it will become 1.64. So the ratio of the central line velocity in terms of this laminar and the turbulent flow will be 1.64. So the final answer, we can write it as 1.64 up to 2 decimal places. So in the first question that we saw today, we had to basically find the ratio of the maximum velocity for the two different kind of scenarios given here. So first was for laminar flow and the second case was turbulent flow. So we looked on to that. So basically we first used the continuity theorem to calculate the average velocity in both the pipes, and then we had the correlation relating the average velocity to the central line velocity or the maximum velocity that we used to find the desired ratio. Now the second question is related to Bernoulli's theorem. This is question number 35 from GIT 2016. The question is, water with a density of 1000 kg per meter cube is pumped at a rate of 36 meter cube per hour from a tank 2 meter below the pump to an overhead pressurized vessel 10 meter above the pump. The pressure values at the point of suction from the bottom tank and at the discharge to the overhead vessel are 120 kilopascal and 240 kilopascal respectively. All pipes in the system have the same diameter. Take acceleration due to gravity, g is equal to 10 meter per second square. Neglecting frictional losses, what is the power in kilowatt required to deliver the fluid? So in this question, we have been given a pump and a tank, and we have been asked to find the power required by the pump to deliver the fluid to the tank, which is 10 meter above the pump, and the suction point is 2 meter below the pump. So let's take a look on the video solution. Solving question number 30. Overhaul to the overhead acceleration due to if this is the pump, so suction will be at the bottom of the pump, and this height is 2 meter. Then the discharge is at the tank at the overhead pressure vessel 10 meter above the pump. If this is the tank, then this height is 10 meter. Then the density we have been given as 1000 kg per meter cube, and the flow rate Q dot is 36 meter cube per hour, and the pressure values of the suction from the bottom of the tank, that is at this point. At 1 we have the pressure value of 120 kilopascal, and at discharge, that is at second point, we have the pressure of 240 kilopascal. So all the pipes have same diameter, and the value of G is 10 meter square, 10 meter per second square, and we have to find the power required to deliver the fluid. So we can write the energy balance across the system, and it will result in the Bernoulli equation of the for P2 minus P1 upon rho plus half of V2 square minus V1 square plus G H2 minus H1 plus summation of F plus shaft work is equal to 0. Now, in this question, we have been given all the pipes in the system have the same diameter. That is, the velocity of the fluid at 1 and 2 will remain the same. So we can cancel the second term. Now we will be having pressure head due to this height difference of 10 plus 2, that is 12 meter. We haven't been given any frictional force, frictional losses, and have been specified that neglecting the frictional losses, so we can take this term also as 0. And then we have to find this work from which we can find the power required to deliver the fluid. So we can replace the values over here. So P2 we have been given as 240 and P1 as 120 kilopascal. So we will keep the units as kilopascal only. So it will become 240 minus 120 upon rho is 1000 plus G is 10 10 into H2 minus H1 is basically 10 plus 2 will be 12 plus shaft work is equal to 0. Now this was in kilopascal, so we can change it into pascal by multiplying it by 1000. So ultimately this will the pressure will be in pascal upon the density, so that will become, let's just write this as 240 minus 120 is 120 plus 120 is equal to, you can write it as work. So this will be equal to 240, it will be kg per meter cube and pascal. So the units of this work will be joule per kg. So the work required to shift the water from by the pump will from the to the height of 12 meter from the suction point will be 240 joule per kg. Now the power required, we can write this as mass flow rate into work. The mass flow rate we have to find it in kg per second. So since we have been given the flow rate in 36 meter cube per hour, we can change it in kg per second as Density is 1000 kg per meter cube, so 36 meter cube will be equal to 36,000 kg. And over we can change it into second as 3600 second. And then the work we found out to be 240 joule per kg. So ultimately we will be having 2400 joule per second as the power. So this is equal to 2400 watt, and we have been asked to find the power in kilowatt. So the power in kilowatt will be 2.4 kilowatt. So the final answer we can select as option B, that the power required to deliver the fluid will be 2.4 kilowatt. So in this question, we saw the application of Bernoulli's theorem, and in most of the questions that we will discuss today, we will be using the same Bernoulli equation and then calculating the work required or power required. So again, this is a very similar question. So this is question number 41 from GATE 2019, and the question is: a centrifugal pump is used to pump water of density 1000 kg per meter cube from an inlet pressure of 10 raised to 5 Pascal to an exit pressure of 2 into 10 raised to 5 Pascal. The exit is at an elevation of 10 meter above the pump. The average velocity of the fluid is 10 meter per second. The cross-sectional area of the pipes at the pump inlet and outlet is 10 raised to minus 3 meter square, and the acceleration due to gravity is 10 meter per second square. Neglecting losses in the system, the power in watts delivered by the pump is dash. Again, let's look on the video solution. This is also similar to the previous question in which we had to calculate the power. We are solving 2019 chemical engineering. So first of all, in this question, we have been given a centrifugal pump. And it is used to pump water with density of 1000 kg per meter cube from an inlet pressure of 10 raised to 5 Pascal to an exit pressure of 2 into 10 raised to 5 Pascal, and the exit is at elevation of 10 meter above the pump. So if this is our suction of the pump over here, let's just call it as 1. At 1, the pressure is 10 raised to 5 Pascal, and the exit is 10 meter above the suction. So if this is the exit, then this will be 10 meter. Let's just call it a second point, and at second point the pressure is 2 into 10 raised to 5 Pascal. Now we have been given that the cross-sectional area of the pipe at inlet and outlet is 10 raised to minus 3 meter square. So area at 1 is equal to area at 2. Both the areas are same as 10 raised to minus 3 meter square. Gravitational constant is given as 10 meter per second square. Neglecting the losses in the system, so it has been given that the frictional losses should be neglected, so we'll just consider it as 0. Then we have been asked the power delivered by the pump is dash. Power we have to find, and power we usually write it as mass flow times of work done by the pump. So over here we can write the mechanical energy balance over this system. That is, we can write the Bernoulli's equation for this system and then we can find the desired terms. So if we consider these 2 points 2 and 1, for that we can write P2 minus P1 upon rho plus G. So over here height is, let's call this as height is h2 and over here height is h1. If this is our reference, we can call this height 1 as 0 and this height 2 will be 10 meters. So let's just write it h2 minus h1 plus 1 upon 2 alpha v2 square minus v1 square plus summation of f plus work done is equal to 0. Now over here we have been straight away given that we have to neglect the losses, so this term will be 0. Now since the area is same from the continuity equation, rho 1 a1 v1 is equal to rho 2 a2 v2, we can say that v1 will be equal to v2. That implies this term will also be equal to 0. Now we have been left with these other three terms, using which we can calculate the work required to transport the water from 1 to 2. So over here we can write that P2 is 2 into 10 raised to 5 and P1 is 10 raised to 5 Pascal. So P2 minus P1 will be 10 raised to 5 Pascal upon density we have been given as 1000 kg per meter cube. Then gravity constant is 10 meter per second square and height h2 minus h1 is 10 meter. So this will be equal to work required. This we can write it as 100 plus 100. The unit will become, over here it is meter, so it will become meter square per second square is equal to minus of W. So this is equal to 200 meters 200 meter square per second square. So the work required we found out as 200, and in the question we have been asked to find the power. So power is defined as mass flow rate times of work done. The mass flow rate we can calculate using this rho AV into W. So density is 1000. Area we have been given as 10 raised to minus 3 meter square. 10 raised to minus 3 meter square into, then velocity is 10 meter per second, and then we have been asked, then we have found out this work, so that is equal to 200. So this we can write it as 2000. So if we write the units over here, it was meter square per second square. Then this velocity is in meter per second. 10 raised to minus 3 is again in meter square. This is kg per meter cube. So basically we can write this as kg upon meter cube into meter square, meter cube upon second into meter square upon second. So this will get cancelled out, and basically kg meter square upon second cube is, you can call it as watt. So this is basically watt, 2000 watt. So the power required, the power delivered by the pump is 2000 watt. So we can write the final answer as 2000 watt. In this question, we again use the Bernoulli's theorem to calculate the power required by the pump. Now we will be looking into few other questions not related to the Bernoulli's theorem. So this is question number 36 from GATE 2020, and the question is: a student performs a flow experiment with a Bingham plastic under fully developed laminar flow conditions in a tube of radius 0.01 meter with a pressure drop of 10 kilopascal over tube length L of 1 meter. The velocity profile is flat for R is less than RC and parabolic for R is greater than RC as shown in the figure. Consider R and X as radial and axial direction, and the shear stress is finite as R approaches 0. A force balance results in this equation where tau Rx is the shear stress. If RC is equal to 0.001 meter, the magnitude of yield stress for this Bingham plastic is dash. So from the power law model, when we were discussing about this fluid statistics, we studied that the Newtonian fluids follow such a kind of relation between the shear stress tau and the shear and the strain rate. If this is the strain rate, then for Newtonian fluid, they are directly proportional. Whereas in case of Bingham plastic, we can also write this as tau is equal to tau naught plus mu dV by dy. So this is the yield stress only if the shear stress is above this value, then the fluid will start to flow. And when the fluid will start to flow, we will be seeing such a kind of parabolic profile. And if the fluid is not flowing, then the flow will be simply constant, or it will be straight line. So in this question, we have been asked to find the value of this tau naught. That is the yield stress for this Bingham plastic. So let's take a look on the video solution. Solving question, the figure. C is 0.001 meter, then the magnitude of yield stress for this Bingham plastic in Pascal is dash. So over here we have been given the velocity profile of the Bingham plastic. So and here we can see that this is the radial direction and this is the axial direction. And until this R tends to for R less than RC, we are having this constant velocity profile. And if R is greater than RC, then we are getting somewhat kind of parabolic velocity profile. That implies that beyond RC, there will be what the shear stress is sufficient enough to develop for the Bingham plastic to fluid. That implies that at R equal to RC, there will be this yield stress above which the Bingham plastic will start to flow. So basically, we have been asked to find the shear stress at RC, that is the yield stress tau naught. So for that, we need to find the relation between the shear stress tau Rx with respect to R. This tau is a function of R. So what we will do is we can simply integrate this equation and get the desired relation. So to integrate this equation, we can write this as integration of d into R into tau Rx is equal to integration of R minus delta P upon R into dr. So if we integrate this, we will be getting R tau Rx is equal to delta P upon L will remain constant integration of r will be r square by 2 plus some constant. So we can also write this as tau rx is equal to minus of delta p upon 2l r plus c upon r. Now from the given information, we need to find the value of this constant c. So in the question, we can see that we have been given that the shear stress is finite as r approaches 0. That is, as r tends to 0, tau will become finite. Tau rx will become finite. So we can put r equal to 0 in this equation. So if you put r equal to 0, this term will become 0. So, and since this is finite, that implies c must be 0 for this equation. So for both the sides to be finite, that implies the value of constant c is 0. And from this, we can get the correlation as tau rx is equal to minus of delta p upon 2l into r. So now we have to find tau naught, which is basically tau rx at rc. So tau rx we found out as minus of delta p upon 2l into r. So if you put r equal to rc, then we will be getting the yield stress, that is tau naught. So delta p we have been given as 10 kilopascal and length we have been given as 1 meter, and critical rc is 0.001 meter. So delta p was 10 kilopascal, the length is 1 meter, radius is 0.001 meter. So this unit will get cancelled out, and we will be having 5 into 10 raised to minus 3 kilopascal. That implies the yield stress, if we neglect the sign, so it will be 5 Pascal. So the final answer, that is the magnitude of yield stress for the Bingham plastic, is 5 Pascal. So in this question, we calculated the yield stress required for the Bingham plastic in order to flow. So we were given a force balance equation, and by integrating that, we found out the relation between the shear stress versus the radius, that is basically tau as a function of r, and using that we calculated the yield stress tau naught. Now this question is again the application of Bernoulli's theorem, and it is very similar to the previous questions that we discussed, so we can skip this question. We can take a look on this question. So this is question number 22 from GATE 2021. So the question states that consider a steady flow of an incompressible Newtonian fluid through a smooth circular pipe. Let alpha laminar and alpha turbulent denote the kinetic energy correction factors for laminar and turbulent flow through the pipe. For turbulent flow through the pipe, alpha turbulent is given as V bar. This equation here, V bar is the average velocity, V naught is the center line velocity, and N is a parameter. The ratio of the average velocity to center line velocity for the turbulent flow is for a turbulent flow through the pipe is given by this equation. For n equal to 7, the value of alpha turbulent upon alpha laminar is dash. So over here we have been given the equation that correlates the kinetic energy correction factors with this ratio of center line velocity to the average velocity and this parameter n, and then we have been asked to find the ratio of the kinetic energy correction factor for turbulent flow and laminar flow for given value of n is equal to 7. So we have been asked to find alpha turbulent upon alpha laminar. So for laminar flow, we can remember that the value of the kinetic energy correction factor is always 2. So for laminar flow, we can always write alpha equal to 2. And same we use this in Bernoulli's equation also in terms of this velocity term. And for alpha, for turbulent flow, this alpha value will depend on many factors. So that is being captured by this equation. So for n equal to 7, we can use this equation to find the value of alpha turbulent, and then we can simply divide it by 2 to find this ratio. So first we can calculate this value ratio V bar by V naught for n equal to 7. So this will become 2 into 7 square will be 49 plus 7 plus 1 is 8 plus 2 into 7, 14 plus 1 will be 15. So this is basically 98 upon 120. So 98 upon 120 will be 0.8167. So this value is 0.8167 that we will replace over here. It will give us alpha turbulent is equal to 0.8167 whole cube into 2 into n square is 49 upon 7 plus 3 is 10 into 3 plus 14 basically 17. So this ratio will become 0.544 into 98 divided by 1070. We take 2 into n square plus n plus 1. N is 7. Over here it will be 8 plus 2 7s are 14. Now this will eliminate. So this is 2 n square. N is 7. 7 plus 3 will be 10 plus 17. So this will be this is coming around 0.3136. Where are we making the mistake? So over here we have this value of point. So this we calculated as correct. Now this is 2 into 4. This comes around 0.3136, and if we divide this by, for this ratio alpha turbulent upon alpha laminar, we can divide this by 2 and it will be 0.3136 divided by 2. The value comes around 0.1568. Alpha t upon alpha l is 0.1568. So the final answer is not this one. The final answer will be 0.1568. So I will correct this solution and upload the video solution. So this is the incorrect answer. So in this question, we simply had to replace the value of n equal to 7 in this equation in both of this equation. And for alpha laminar, the value of this kinetic energy correction factor is simply 2, so that we can straight away replace. Now let's take a look on this question. So this is question number 38 from K 2022 chemical engineering paper. The question is, a horizontal cylindrical water jet of diameter d1 is equal to 2 centimeters strikes a vertical solid plate with a hole of diameter d2 is equal to 1 centimeter as shown in figure. A part of the jet passes through the hole and the rest is deflected along the plate. The density of water is 1000 kg per meter cube. If the speed of the jet is 20 meter per second, the magnitude of horizontal force in Newton required to hold the plate stationary. So we can take a look on the video solution. So question number 38. This is question number 38 of chemical engineering paper. Question is related to fluid mechanics. Of diameter 1 centimeter. So over here we are having a hole of diameter 1 centimeter, and the part of the jet passes through the hole and the rest is deflected. So basically this much passes through and the other part of the fluid is deflected. And then we have been given the velocity, that the speed of the jet is 20 meter per second, and then we have been asked to find the magnitude of horizontal force in Newton required to hold the plate stationary. That is, we have been asked to find the force. So for any system with flow, we can write the summation of force will be the change in the momentum flow rate. That is change in momentum flow rate. So let's just consider at this as point A and this as point B. Then we can write this force as MB minus of MA. Where basically this MB, we can MB or MA are this M dot into velocity. That is basically mass flow rate times of velocity. Or we can also write this as rho A V and again V. So this will become rho A times pi by 4 d square into velocity square. So this is the formula for momentum flow rate. So at point A, we can write this MA as rho is 1000 kg per meter cube. 1000 into pi by 4 into diameter is 2 centimeter, 0.02 whole square, and the velocity is 20, so it will be 20 square. So this will become 1000 into pi by 4 into 4 into 10 raised to minus 4 into 4 into 10 square. So this will get cancelled out. 10 raised to okay, well, here we are having 1000. So this will be 40 times of pi. So MA is 40 times of pi. Similarly, we can find this MB. So at this B point, the diameter is getting halved. So over here, the diameter was 2 centimeter, and at point 2, the diameter is becoming 1 centimeter, whereas the velocity will remain same throughout. So since the diameter is getting halved, the momentum will be 1 by 4 times of that present at A. So basically MB will be 10, basically 40 pi upon 4. So that is MB will be 10 pi. So the force exerted by the jet to keep the force required, basically this force required to hold this plate stationary due to this effect of this water jet will be, we wrote it as mb minus ma. So this will be 10 pi minus of 40 pi. So this is minus of 30 pi. So the force required is 30 pi. So from the given option, we can select option A as the correct answer. Just give me a minute. Hello. हेलो. हाँ आया मैं. So in the last question that we discussed right now, we calculated the force required to keep this plate steady. So basically we were having a plate and then this water jet was applying the pressure in this direction. Then we had to find the force required in this direction, basically to keep the plate stationary. So that we had find by using the force balance. So these two questions we can discuss it in next class. So this question is related to boundary layer theory, and then we will be covering few of these instruments, venturimeter, pitot tube, in the next class. So in today's class, we discussed most of the questions related to this Bernoulli's theorem that were used to calculate the power required to deliver the fluids to some location, or the power delivered by the pump. And then we use this kind of this force balance equation, and then one more question related to this Bingham plastic. So that was all for today. If you have any doubts, you can write it in chat box, or we can end today's session. Okay, so we are ending the class a bit early today. We can cover up in the next class. So thank you for joining. Bye.